In this video, we're going to go through energy forms and uses. We're going to look at some exam questions that have come up previously before. So a metal ball which is tied to a string swings from A to B and then to C as shown below. So from A to B and then B to C. Describe the energy change for the metal ball as it moved from position A to B and then to C. So take note that I want the energy change from A to B. So when the ball moves from A to B, the energy change is from gravitational potential energy to kinetic energy. Alright? Or you can say it actually had maximum gravitational potential energy, and at point B it had maximum kinetic energy. And from B to C, it moved from maximum kinetic energy to gravitational potential energy again. At which position A, B, or C did the ball have the greatest kinetic energy and the least gravitational potential energy? So if you look at the ball, A, B, or C, so greatest kinetic energy is at B, because this is the point where it is moving the fastest. Alright, so also known as having the greatest kinetic energy. Least gravitational potential energy is also at point B, because all the GPE has been converted into KE over here, so it has the least GPE over here, and then over here it has the most GPE and the least KE. Alright, and likewise for this is the most GPE and the least KE as well. Okay, effectively there will be a point where there's 0 KE. There's also a point where this ball will have 0 KE. Why was the height of the ball at C less than 30 centimeters? Alright, so A was at 30 centimeters and C is lower than 30 centimeters because energy was lost to air resistance and heat. And if you want to put it, and sound, if you want to put it. Okay, so you lose energy to air resistance, to overcome air resistance, to produce waste energy like heat and sound. Therefore, not all the GPE is converted into KE at point C, and eventually it will swing and swing and swing and swing, and then to a point that it will stop because all the energy has been lost as to air resistance and also to heat and sound. June made a jumping toy using 2 pieces of strong plastic cards and an elastic band. She wanted to find out how the number of elastic bands used to make the toy would affect the height. So she stretched before she released. The toy snapped and jumped to a certain height, which June measured and recorded in the table below. So repeated the activity by increasing the number of elastic bands. So this is an experiment even before looking at a question. Something to do with elastic potential energy. Alright? Something to do with height and elastic potential energy. So number of elastic bands used from 1 to 5, height that the toy jump. Okay, so let's take a look at the question. June recorded one of the results wrongly, put 1 cross in the box to indicate the mistake she made. So as the elastic bands go higher, you should expect the height of the toy to jump to go higher, which is correct. So 6, 9 is correct. Oh, 5 is something wrong. Then 13, 16. So 5 is the one that is something wrong, because you should not be expecting from 9 to 5. You should be expecting from 9 to more than 9 and less than 13. Suggest what June could do to ensure that her results were reliable. So standard one, what you can do to ensure your results are reliable is to repeat 3 times, repeat the experiment for 3 times and find the average. Alright, so that's a standard answer. Every time they ask for this, repeat 3 times, find the average. Gary made a paper flyer using a strip of paper and paper clip as shown below. He wanted to find out if the number of paper clips on the paper flyer would affect the time it would take for the paper flyer to fall to the ground. So what is the experiment trying to do? It's the time it took for the paper flyer to fly to the ground and find out if the number of paper clips. Alright, so this, you should know immediately that this should be your variable and the time it took should be your measured. Alright, so this is your changed variable, this is your measured variable. So below are the steps he took. He cut out bliss, attach one, drop the height from 5 meters. So everything else except this should remain the same, no matter what happens. Same paper, same height, same number of, different number of paper clips because that's the changed variable. But everything else should remain the same location, same time, blah, blah, blah. What did Gary have to measure after dropping the paper flyer? So he has to measure the time it took. All right, measure the time it took to reach, for the paper flyer to reach the ground. Okay, so that's what you can do to measure the time it took for the paper flyer to reach the ground. Name one variable that Gary must keep constant in his experiment. So many variables, so maybe it's like, for example, is type of paper. Also the location, all right, the location, and yeah, these two are the more reasonable variables to keep constant. So pick either one will do. Explain why Gary had to keep the variable in B constant, whereas is it type of paper or the location? Because he wants to remove, remember these three words, remove the effect of the variable, be it type of paper or the location or the wind or the sun or whatever, on the time it takes for the paper flyer to drop on the ground. All right. Now the key term I want you to remember from this is remove the effect. Okay, you're gonna see a lot of this kind of questions. Explain why you have to keep the variable constant. So you want to remove the effect of whatever the thing that you want to be keeping constant. Okay, you want to remove the effect of that thing on the measured variable. Right, so maybe the type of paper will cause it to fall faster, so you want to remove the effect of the type of paper. Maybe the location will cause it to fall faster because there's some locations got greater wind, some locations got no wind, so that will cause the paper to fall faster. So you want to remove the effect of the wind. So that's how you do it. So remove the effect of that variable that you want to keep constant on the, this is the measured variable. This is basically the measured variable. So on the time it takes for the paper flyer to drop on the ground. So if it's another experiment, just repeat using the measured variable in that experiment. Okay, but I want you to remember this word, remove the effect of the, this is a constant variable on the measured variable. Ashlyn held the toy between her hands. She rotated the toy by sliding her right hand forward, her left hand backwards before releasing it. The toy flew to a certain height after it left her hands. She rotated the same toy again. However, the toy flew to a greater height. Which one of the following explain why the toy flew to a greater height? Now, basically, if you do this and the toy flies a certain height, and you do it again and the toy flies another height, generally there is more, more force using your hands, all right, more energy, more kinetic energy of your hands. That's why it transferred to the kinetic energy of the paper or the flyer going upwards. Which one of the following could explain the weight of the toy was lesser? That's wrong because it was the same toy, so it cannot be the weight of the toy lesser. The toy used up more heat energy. Wrong. There's no heat energy that's being used. Kinetic of the energy of the toy was greater. Correct. Kinetic potential energy of the toy was lesser. That's not correct. Okay, because the toy moved from the KE of your hand is transferred to the KE of the toy. So because your KE of your hand higher, then the KE of the toy higher, then therefore it will go higher. So kinetic energy of the toy was greater is the correct answer, because the kinetic energy of your hands are also higher. The diagram below shows a waterfall. Which one of the following correctly describes the energy of the water at A, B, and C? So energy of the water at A, B, and C, even without looking at it, right? So water, you know, got max KE. Sorry, what am I talking about? It should be maximum PE, all right, potential energy. At the bottom will be maximum KE, all right, in the middle is half-half. So which one of the following? A, KE, KE, PE, and KE, PE, and KE. So this two is correct, because there is KE moving the water down. There's also PE of the water. So at B, PE and KE correct. PE and KE correct. KE and sound energy correct. At point C, heat energy, nope, not really correct. Point C should be KE and sound energy correct. Okay, because the waterfall is making sound. So the answer is number 3. A ball was released from point A and moved along the points to point E, where it stopped as shown below. So A, B, C, D, E. Which of the following is correct? The ball had less energy at B than at A, less energy at less KE at B than A. That's wrong. It actually has more KE. It has more KE at B than A. So this point is maximum potential energy. The ball had more KE at C than at D. No, that's right, actually. All right. So more KE at C, because when it goes up, then the KE will reduce, then there will be more PE over here. Okay, because it's going upwards. All the kinetic energy of the ball was converted to gravitational potential energy as the ball rolled to D. That's not correct, because there will be some loss to friction, there will be some loss to heat, there will be some loss to sound, there will be some loss to air resistance as well. The kinetic energy of the ball was converted to only sound energy at C. That's not correct, because it's also converted to friction, heat, and sound, and all the others. So the answer is number 2. Which one of the following are examples of energy conversion? Walking to a classroom, yes, is from chemical potential energy of your body to kinetic energy. All right. Switching on a torch, yes, it's also from chemical potential energy of the battery to light energy. Using petrol to drive a car, also correct. Also chemical potential energy to kinetic energy plus heat energy from the car. A, B, C, number 4. For a balloon which remains suspended in the air as shown below. Height of the balloon from the ground was measured as the speed of the hairdryer was changed. The results were recorded as shown below. So the height, first reading is 28, low for speed, medium, high, low, medium, and high. And then you have 28, 30, 29, 29. Medium, it's a bit higher, high, it's a bit higher. What is the relationship between the speed of the hairdryer and the height of the balloon from the ground? So remember, when you see this kind of relationship question, it's always the more, the more, or the less, or the less, the more, or the more, the less. Okay? So what's the relationship between the speed of the hairdryer? So the higher the speed of the hair dryer. So again, when I say the more, you don't have to write the more the speed, right? Grammatically, please make your sentence sound correct. So when I say the more, it's like equivalent to like the higher the speed of the hair dryer, comma, the higher the height of the balloon from the ground. The higher the height of the balloon from the ground. All right. So again, grammatically, let your sentence make sense. So it's not the more the speed of the hairdryer, the more the height of the balloon from the ground. Okay. So tweak it such that it makes sense. That's all I'm saying. All right. It makes grammatical sense. But in essence, the meaning is this part is actually the more, and then this part is also the more, the more. Okay, so this answer is one of the more kind of question or answer. Explain the stated relationship in A. A is this one. In terms of energy conversion, so in terms of energy, so greater KE of hair dryer will lead to greater potential or gravitational potential energy of the balloon. Alright, so that's the energy conversion. So the kinetic energy of the hair dryer is converted into the gravitational potential energy of the balloon. On to keep the balloon suspended in the air. So you have electrical means is electrical energy is converted to kinetic energy plus hot air. So you have heat energy plus GPE of the balloon. The diagram below shows how a swing moved from the start position A to B and then to C. So A to B and then to C. It's quite a common diagram. So A will have maximum PE or GPE. B will have maximum KE. C again maximum PE. So potential energy from A to B, so maximum PE to maximum KE, so potential energy will be from maximum to 0 at KE, so it is decreasing. Kinetic energy from B to C, so kinetic energy is maximum here, is 0 over at C, so therefore it is also decreasing. Alright, so the answer is number 4. So again, I explain again. So this is maximum PE, and over here it is minimum PE. So therefore, from maximum to minimum, it is a decrease. Maximum KE, over here is minimum KE. Therefore, from maximum to minimum, also a decrease. So this is a decrease. And the diagram below started her dive standing at point W, which is over here. The arrow traced the path, so she moved from here to here to here. Based on the diagram above, at which point in her dive was elastic potential energy converted to kinetic energy? So is it here when she ran? So she ran from here to here. It's actually chemical potential energy from the body to kinetic energy. And then at this point, she will jump up, jump down, and lift up, and come down. Alright, so jump up and down and lift up. So it's actually the, what is this? Elastic potential energy of the board go up into potential energy into kinetic energy. Okay, so at which point in the dive was elastic potential energy converted to kinetic energy? So it is point over here. It's point here because after I jump down, I will jump up. So I convert the elastic energy into kinetic energy to go up. Alright, so this point X is the point that the elastic potential energy is converted to kinetic energy. Okay, so this is a very long question. You can read it yourself first. Okay, he made a toy using some wire, rubber band, and a ring. Attach the ring to the end using 2 rubber bands. So basically there's a ring here. If you turn the ring many times, then you will turn the rubber band many times. So what is this? This is actually elastic potential energy. Okay, if you have not read this question, pause the video and go and read this question first. So Jack turned the ring 5 times, blah, 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 blah. He carefully played, blah, blah, blah. So when the thing unwound itself, alright, when the thing unwind itself, then you will hit a card over here and it will make some sound. Alright. So honestly, I don't know why he picked this toy. It doesn't seem very fun. I just want to make some sound from the card. And it will make some sound. So complete the main energy conversion for the toy before the card was opened to the time it unwound and hit the sides of the envelope. Potential energy. Converted to energy of ring when rubber band unwind. It's kinetic energy. Energy of ring hitting the card is something plus something, so it's actually sound. Sound is the obvious one, right? So sound energy. And the next one is actually not so obvious, but whenever something hits something or there's something touching each other, there's always friction. Alright, and friction will cause this thing called heat energy. Okay, so energy of ring heating cut is actually heat energy. So just to go through again, elastic potential energy of the wound up rubber band will change into kinetic energy of the ring when the rubber band unwinds, because it will start turning very fast. So that's kinetic energy, and then it will hit and produce sound and heat energy because it touches the rubber card, the card, so there will always be friction, and friction causes heat. Became louder when Jack turned the ring 10 times. So again, 10 times explain means you have a initial condition. So turn 10 times will lead to some things and then become louder. Alright, become louder is the final condition for the final state. 10 times you increase the elastic potential energy. When the elastic potential is increased and he lets go, there will be increase in the kinetic energy. When the kinetic energy is increased, then therefore you will hit the cut with a harder force, and therefore it will increase the sound energy, which will make it appear, as in make it sound louder. Alright, so that's the thing. So again, I repeat, turn 10 times, increase in elastic potential energy, which will increase the kinetic energy when you let go, harder force, which will hit the paper, which will hit the paper with a harder force, and then it will increase the sound energy, and therefore it will become louder. So the key thing to note again, this is a explain question, therefore you need to write the first part, the first condition, which is turn 10 times, Jack turned the ring 10 times. Final condition, which is become louder. So explain why the sound became louder. So it's always explain why something became blah blah blah. The blah 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 is always the final thing. When you do something, the something is always the initial thing that you do. Alright. So you have your scientific explanations must link the final to the initial. Key to wind up the spring. After 3 turns of the key, the spring became stuck, could not unwind, the toy mouse could not move. What inference could Gopal make regarding this observation? So the spring became stuck, could not unwind, and the toy mouse could not move. Alright, so the spring had lost its energy. Is it true? It's not true. It's just the spring got stuck. So the spring still has the elastic potential energy. It's just that it cannot release the elastic potential energy because it got stuck. The potential energy has been converted to sound energy. This is not correct at all because the potential energy is still within the spring. The potential energy of the spring could not be converted to kinetic energy. That's correct, because it's stuck there. Maybe the toy is spoiled. Gopal had destroyed the energy. Wow, when he turned the key too hard. Energy cannot be destroyed. It can only be changed from one form to another. So he did not destroy the energy. The energy just got stuck there. The spring got stuck. So the energy, the elastic potential energy is still there. Alright, it's just not released yet. So the correct answer is number 3. The diagram shows a catapult that will hit a target when object A placed at the end of the elastic band is released. So this is object A over here. Which of the following factors will affect the distance traveled by object A? Mass of object A, yes. So the greater the mass, the shorter the distance, because there will be more gravitational force acting on it. Material of the stick used. So this is not true, because if it's made of plastic or if it's made of metal, it doesn't really matter, just as long as it's stiff enough to withstand the force of the elastic band. So it doesn't matter whether it's plastic or metal or wood. The distance the elastic band is pulled back, yes. So this will affect the distance traveled by object A, because the greater the distance, what's the relationship? The greater the distance pulled back, you will have greater what kind of energy? Elastic potential energy, and therefore it will be converted into kinetic energy, and the greater the kinetic energy it will be converted to, alright, and it will go the greater the distance, that is, it will fly. So therefore the answer is actually A and C, which is number 3.